So, this is the simplified resistance spot welding thermal cycle, but life is not that simple. So, we love to introduce some complexity to attain various the modification in terms of microstructures as well as the nugget geometry. So we can based on the automation of your resistance spot welding equipment, and we can introduce various modified weld thermal cycles during welding. For example, one such modified enhanced weld thermal cycle is shown in this diagram. So we were looking at in a previous simplified case, we have a squeeze time where we start applying the load, okay, over here, and then we started applying current, and subsequently we stopped passing the current, and then we release the load, we form the weld nugget. But we can introduce various heat thermal cycles. And for example, in welding, so we also sometimes like to apply a preheating thermal cycle. Okay, so that can also be introduced. For example, you start applying a load initially to keep the fairing interfaces in its position, and then instead of passing full current, the amperage, so we can also apply a small short pulse, okay, in order to preheat your workpiece, your sheets. And then so upon keeping for some time, we preheat a pre-weld interval, for example, and then we can start applying the current, not as in a single pulse. We can also have a ramping up current where you gradually heat up your welding sheets to a temperature of above the temperature of melting, and then during this process you can also either apply a pulse or a constant amplitude. Okay, so we can have a one upslope, and then we have a constant current and impulse, and then we can have another downslope, and doing so we can also modify the heating and then holding and then cooling time, and subsequently the rates at which these weld nuggets are heated and then cooled. Okay, and then the entire weld time is determined by the upslope, and then the current we apply at the constant amplitude, and then downslope. Okay, and during this process we can also have a cooling time in between. So you form heating up, and then you maintain some interval, and then apply another current, and subsequently you can also have another interval between applying a peak current. And there are various reasons we can use these modified weld thermal cycles, because we can also control the heating rate, and we can also control the nugget geometry, and we can also control the cooling rate at which the weld nugget that is formed at the interface is cooled. And then after that, after passing a current, you can have so we can also increase the load upon cooling, and that can also control your stress development, residual stress development, because we are introducing compressive stresses, right. So when the transformation is happening, we can also apply compressive stresses to mitigate the residual stress, okay, during cooling. And subsequently, upon cooling to room temperature, we can also apply another pulse, okay, and which can heat treat the whatever weld microstructure that is formed after the first cycle. And for example, if you have a fully monatomic microstructure, we can also use a temper time, which is actually in which we pass some amount of amperage to have a tempering of the monatomic structure that is formed upon welding. And then yes, you can also have a ramping downward, or we can also ramp up during this process if you want to change the stress state of your weld. So everything is possible, and the entire cycle can be completed within a second or so, or even not more than a few seconds. So the entire thermal cycle of a weld nugget formation can be altered based to our needs. For example, as I had explained, if you want to have a tempering of your weld nuggets, we apply a small post pulsing current, or if you want to reduce the cooling rate at which the welds are cooled after welding, and you can also do a preheating by applying some short pulsing before the application of the actual the welding current. and you can also change the loads based on our need. So, in this case a typical cycle, and we also have an increasing load when the weld nugget is cooled to mitigate the residual stress. Okay. And all of them can be used to in our favor to modify the weld thermal cycle. Okay. And the commercially used the resistant spot welding, and nowadays they have capability to generate such a complex waveforms, complex interplay between the load as well as the current, which can be used to modify the microstructures or to generate microstructures which are actually superior than even a base material. Okay. So, to summarize the weld cycle, the pre-compression process are used to set the electrodes and workpieces together. Okay. So, you can apply a preheat to reduce the thermal gradient at the start of the weld time, or to soften coatings such as, for example, galvanized coating. And the forging force is to help to consolidate the weld nugget, and the quench and tempered seams are used to produce the desired microstructure. For example, in the ice and steels, advanced ice and steels, the cooling rates that are actually used in resistant spot welding would invariably lead to the metastatic microstructure. So, we can use a post pulsing either to temper the metastatic microstructure, or we can also remelt the weld nugget that is formed in order to homogenize the segregation. So, that is also really helpful in some of the alloys, which we will see in last classes, how the modifying weld thermal cycle, especially post pulsing, would help in changing the segregation effects in a resistant spot weld during the resistant spot welding of advanced ice and steels. Okay. And then for example, in post pulsing can also be used to change the weld nugget grind size and improve the strength and toughness. So, there is also current decay. Okay. So, in a downward slope is also used to retard the cooling of aluminum alloys during solidification, change the cooling rate so that we can avoid the cracking. If you generally the aluminum alloys are not considered for resistant spot welding because of the various problems, inherent problems that are associated with aluminum alloys. So, similarly for stainless steel as well, stainless steels are also considered difficult or unsuitable candidate for resistant spot welding. So, generally if you look at, to summarize, as I already explained, so the enhanced thermal cycle can be used to mitigate the stress as well as to change the microstructures in our favor to improve the weld metal properties. So, this slide shows the typical single phase alternating current spot welding circuit. Okay. So, we have a single phase power, and which is capable of producing the current of required amperage. So, the rating of the resistant spot welding machine would tell you how much amperage we can go under maximum, and that will indeed determine the maximum thicknesses that can be welded by a machine. So, we have that the power source contains a transformer, it's a transformer, and which is actually connected to a throat. And generally it is a flexible conductor. A horn is connected to a flexible conductor to get the current from the transformer, which is passed to the electrodes of copper, and subsequently when you pass a current, you have a heat generation by Joule heating. So, the components of the power source as well as the setup is and we have a transformer, a horn, and a cantilever which is actually not only used to pass a current as well as to apply load. Okay. And then we have an electrode attached to the end of this horn, and then your sheets are kept in between the electrodes. Okay. And the horns, so in a typical resistant spot welding cycle, these horns are replaced with robotic arms. Okay. The robotic arms can also control the application of load and the movement of the electrodes with respect to the welding positions. Okay. So, the effect of thicknesses on the heating mechanism should be also considered when you are actually applying when you are using resistance spot welding to sheets. So generally it is governed by the simple equation. So this equation gives the minimum temperature rise that can be obtained for a given mass of M. Suppose if you have a thickness of so and so and you can know how much Q you need to generate for a given thickness, because then you can calculate the M, the mass from the density and volume. You can derive at the mass, and then Cp is the specific heat capacity. Okay. Suppose if you want to increase the temperature delta T, okay, for a given mass of material with a specific heat capacity of Cp, okay, so the Q is the heat you needed to raise the temperature, for example, from 30 to 1500 degrees centigrade. So how much Q you need and for a given mass of material M and then Cp, that is the minimum value. You always underestimate here because of some specific issues with this equation, but that will give you the minimum Q needed, okay, to raise the temperature from, say, for example, 30 to 1500 degrees centigrade. And Q, you already know that from I square RT. Okay, T is your welding time, time at which you pass a current of I, right, and then R is nothing but the summation of all the resistance. So ideally you can neglect these through, and if you know the R2 and R4, we can calculate a Q. Okay, so for a given M mass of material Cp, if you want to increase the temperature from 30 to 1500 degrees centigrade, and we can calculate how much Q we need. Okay, so and then from there we can calculate how much amperage you typically need if you know the R4, or if you send the so much amperage, you can also calculate what is the value of R4, the total resistance. Okay, so that is the mass effect generally we considered. So obviously if you want to weld thicker sections, and you will have to get more Q for same increasing in temperature. Okay, because the Cp is a function of composition, material composition. So we can also calculate a minimum Q needed to increase temperature from T to delta T. Okay, so the other important thing I want to note down here is the units here, amperage. So you should always write, and when you mention amperage and volt, and A and V must be in capital letters. Okay, similarly for ohms, because they are names. Okay. So this slide shows the typical temperature evolution when you are doing resistance spot welding when the current is at the I max, the peak current. Okay, so the sheet thickness is roughly 1 millimeter. Okay, and you are applying a current. So you see the typical distribution of the temperature. So here the dark region denotes the molten material. Okay, so the temperature is higher than 1500 Kelvin, 1500 degrees centigrade in this case, centigrade. Okay, and then so you have a molten region, and the temperature, if you go away from the boundary between the liquid and this adjoining area, decreases very drastically because of the heat transfer, effective heat transfer. Okay, and that will lead to a steep temperature gradient. The temperature gradient will be extremely steep. So you start from a melting point to a room temperature, and in this case, if you have say 1 millimeter thick plate, and within a millimeter, so there is a very steep temperature gradient always present in the resistance spot welding, and so you also cool such a geometry, such a heat mass, and extremely rapid cooling rates. Okay, so typically in this case you will have weld nugget size of about 5 millimeter in these sides roughly. So this is your combined sheet thicknesses of 2 millimeter. and within say 5 millimeter region, so you have a well nugget formation, and then you have a heat affected zone, and subsequently you move towards the base material just by a millimeter or so. So the temperature gradient is extremely steep in a resistance spot welding case, and so that will always trigger to a columnar or the columnar grind growth during solidification. Good. So if you look at the temperature actual thermal cycle extracted from the previous diagram, if you look at it, say for example at the center and the edge of the well nugget which is formed. So a typical well thermal cycle looks like this. So well center, and then and the weld edge which is at the fusion boundary. If you look at it, the actual thermal cycle, so not more than 500 milliseconds. So within 500 milliseconds the material is heated up to temperature and as high as 2000 Kelvin, something around 1700 centigrade, and then cool to room temperature and within a second. Okay. So that means that your cooling rates are roughly in this case about 1000 Kelvin per second. So in this case even higher. So we are cooling it in both the regions. If you look at it, the melting point, if you look at it over here, so you have a complete molten regions between the well center and weld edge, and both of them are cooled at the same cooling rates during cooling. So this is the typical well thermal cycles we adapt during resistance spot welding. And as I already explained, because of the steep temperature gradients that are present in the well during solidification, and you will have well nugget solidifying in a very columnar structure. For example, you have high temperature at the weld interface because of the contact resistance, right? And then your solidification, the moment you form a liquid, and subsequently if you stop the current, then your well nugget would start solidifying, and from the nucleation from the fusion boundary, and then the grinds would grow in a columnar manner towards the well center line from the fusion boundary, and they will coalesce at the well center line. And this structure is not metallurgically preferred because of the very strong segregation that are developing during solidification of the columnar grinds. And during this process, if alloying elements prefer to segregate to liquid, and they will end up enriching the grind boundaries or solidification grind boundaries, these boundaries as well as a well center line. Okay, and because of that, the solidifying grind boundaries and the well center line would be enriched in alloying elements by making these boundaries and the well center line very brittle. And so this structure, apart from the segregation and the columnar solidification, at this location you also have an weld boundary, and you also have an unwelded sheets that are actually act as a stress risers at this point. So that may also cause some problem during loading. We will see in detail the effect of the weld edges in subsequent classes right now. And because of the steep temperature gradient and the heat transfer that are happening by the water cooled copper electrodes, so you trigger a columnar solidification of your solidified liquid when the liquid is solidifying, and due to that you will have a very strong segregation of alloying elements on the grind boundary and the well center line. So the typical microstructure, if I can redraw again, so you have a well nugget, liquid, and so this is your well center line, and then you will have solidification nucleating from the fusion boundary and then going towards the well center line, and during this process you also partition the alloying elements towards the solidifying towards the unsolidified liquid, thereby the liquid at the well center line getting enriched in alloying elements. So, these are typical solidifying microstructures of the resistance spot welds. So, these two micros show the actual micrographs made from DP 800 welds. You see over here, so what I see, so this is 1.2 mm DP 800 sheet, and they are spot welded typically, and what you see over here is your weld nugget. So, it is completely molten and solidified. So, this is a typical weld nugget, and if you zoom in, you see the columnar grain growth solidification, okay, towards the weld center line, and the subsequent to the fission boundary you have a heat affected zone, and in this case it is also clear, right. So, the heat affected zone is somewhere up to this region. Okay, so, this is your weld nugget, and typically, so this is your heat affected zone. And you also have a complete monazite transmission here because of the cooling rates that actually we apply during resistance spot welding. We do not apply, but it actually cools at extremely rapid rate. Okay. And these black dots here is irrelevant, we just harness measurements we carried out on these wells. So, some of the electrodes that we use in resistance spot welding, and we can use various geometries of the electrodes, and it is all governed by the ASM or ISO standards. And if you look at the typical cross sections, maybe in next class I will bring an example electrode. There are various types we can use, and most of the materials are made of copper, and some copper alloys are also used. They are alloyed with copper alloyed with zinc and tin sometimes are also used, and predominantly the electrodes are made from pure copper, and this is a typical cross section. And for example, a point A electrode, type A electrode is in the pointed type. So, this is a face, and there is a channel inside which is used to circulate the water for extract heat. And so, we have various types of electrodes based on the ISO standards. Type A is pointed, type B is dome type, and you may also use a flat electrodes or eccentric electrodes, and type D or truncated electrodes, which is most commonly used in automotive applications. Or we can also use some sort of radius electrode where you have a pointed edge as well as some the concave geometry. So, the most commonly used electrodes are the type E and type B in automotive applications, but based on the various nugget sizes, one can change the electrode shapes, and based on the standards we can choose the electrodes and we use it. Okay. So, the actual standard that governs the electrode is the ISO 5182, you can refer it and then see how these electrode size and shapes can affect your nugget geometry. Okay. To summarize this class, so we looked at resistance spot welding equipment and how the enhanced thermal cycle can be used to modify the weld thermal as well as load cycle in our favor. So, we can introduce a preheating cycle, we can introduce ramping up current, we can modify the heating rate to some extent, we can also modify the cooling rates, by changing the down current after welding, and we can also apply post pulsing to temper the microstructure if we have a fully metallurgic microstructure, or we can also apply a pulse current in order to melt and resolidify the solidified weld nuggets in first place to avoid to homogenize the weld nugget. So the all possibilities are used to obtain the microstructures that are actually suitable for various applications. And then we moved on to the electrode dimensions as well as the equipment that are used in spot welding, and we will continue to look at some of the features of the spot welds, how we can test the spot welds, and how we can change the microstructural spot welds by modifying the weld thermal cycles.